looking now at section 10.5, let's talk about area in polar coordinates. Going back to Cal 1, one of our central ideas that we focus on is the concept of area in an unusual region. We know how to find the area of circles and squares and triangles and rectangles going back to the most basic geometry. But the area underneath an arbitrary curve is a more complicated procedure. And we learn in Cal 1 that the way to do this is using the limit of the Riemann sum, where the Riemann sum allows us to approximate the area, and then by taking that approximation and refining it by taking these rectangles and dropping their width down to 0, typically the limit as the norm of our partition approaches 0, that gives us our integral. So here the area is given by the sum as I goes from 1 up to n of f of x sub n delta x sub n. And here we want to take the limit as n approaches, as the norm of our partition approaches 0. Or you could also say limit as n approaches infinity. Here, that's just the definite integral from the beginning to the end of our interval of our function with respect to the x variable. Well, now we see a different way of expressing a region in space. We see it in polar coordinates. But note that the rectangle is not a natural shape, at least not a simple to express natural shape in polar coordinates. In rectangular coordinates, rectangles are easy enough to build because all you need to do is say, okay, I have a constant and I have a constant here. All right? So that's length times width. In polar coordinates, it's not quite so simple. Well, it is, just not to create this shape. Because here, if I say, okay, I want my x to be bound between constants. X is bound between, let's say 0 and 1. And let's say our y value is bound between constants, let's say 0 and 5. Well, that's a rectangle. All right? Your x value is bound between 0 and 1. And your y value is bound between 0 and, here, let's say 3, because I ran out of space. There you go. And if you say my x value and my y value are bounded by a couple of constants, you end up with a rectangle. It's a natural shape to describe in rectangular coordinates, hence the name of the coordinate system, rectangular coordinate system. But in r and theta, if we're going to describe things using these, having these bound by constants doesn't give you this shape. But it does still give you a recognizable shape. Here, let's consider what happens if r is bound between 0 and 1, and let's say theta is bound between 0 and, let's say pi over 4. Okay. Well, note that theta being bound between 0 and pi over 4 means that you're looking at a region that is between here and here, between the angle 0 and the angle pi over 4. And now saying r is between 0 and 1 means that you're starting from the pole and taking every possible value until you get out to a radius of 1. So the natural shape that occurs in a rectangular coordinate system is a rectangle. The shape that most naturally occurs using constant boundaries in the polar coordinate system is this kind of shape. If you think back to your trigonometry, this is called a sector. And the area of a sector is given by 1/2 theta r squared, where theta, this is important, must be in radians. Okay. Over here, the area is, well, simply base times height. Or even more simply, I suppose, in this setup, it was just x times y. Okay. All right, so here I can approximate an area under a curve using these little rectangles. So in polar coordinates, I can also approximate area, but using, well, this kind of shape. What that leads to is being able to take an area from a polar region, by breaking it up into little tiny sectors. Okay, well, how do we do that? Well, we pretty much already know how. This mimics the exact development of the Riemann sum that we see in Cal 1, but now instead of saying, oh, I have a base times a height, a base times a height, base times height. Now we say, okay, we have an angle and a radius, an r and a theta. But if I take this region here and just break it into little tiny pieces, those little pieces should be sectors. So here, just as a very quick illustration, let's say I simply broke this region here. Notice it's wavy. It's not exactly a sector, but I can break it into 3 sectors that look like this. And now each of those sectors I can find using the area of a sector formula. But then if I add those together, that gives me an approximation. So here, the approximate area, the area in polar coordinates, is approximately the sum as I goes from 1 up to n, how many sectors I have, starting from the first one up to the nth one, of, and it's basically just this right here. It's going to be 1/2 theta r squared. Well, yeah, but theta, if I'm breaking these up into little tiny skinny sectors, this theta is supposed to be really, really small. So yeah, that's an angle, but it's supposed to be a really small angle. So generally, when we talk about something very, very small, a little tiny change in one variable, usually we call it something like delta. Here, a little tiny change in the x variable, delta x. A little tiny change in the theta variable would typically be called delta theta. Okay, so really we could write this as the sum as I goes from 1 to n of 1/2. Here, let me write delta theta. Now remember, there's going to be different thetas, one for each of these. So really I should call it delta theta I. For the first sector, the angle for the second sector, the angle for the third sector. So this is the sum as I goes from 1 to n of 1/2 times r squared delta theta I. Oh yeah, but this r is also going to differ. There's going to be a different radius for each of these sectors. So really this should be r I squared. But notice that r, given the way we've defined polar coordinates in previous sections, r isn't really its own independent variable. It's dependent on theta. Rather, it's a function of theta. So here, since recall, we can usually write r as a function of theta. Instead of writing r squared, maybe we should write f of theta squared. So this is going to be the sum as I goes from 1 to n of 1/2 f of theta I squared delta theta I. Okay, so basically all we've done is we've described, okay, we're going to add together a few sectors. Each one will have its own angle. Each one will have its own radius. Now it's being squared because of the formula of the sector that we see back in trigonometry. R really should be thought of as a function of theta. So here let's write that so that we don't have 2 different variables floating around. So we're just adding together 1/2 r squared theta. But we're adding together a bunch of them. But notice that this mirrors exactly what we develop over the course of several chapters in Cal 1. It's a Riemann sum. Well, essentially. It's in a different coordinate system with a different type of shape, but it's still a sum. And if this is an approximation, well, then we can make that approximation better by making these thinner and having them closer together so that there's more and more of them. So instead of saying that the area in polar coordinates is approximately that, we can say that it's exactly equal to the limit as n approaches infinity, as the norm of our partition approaches 0. When we say the norm of our partition, remember back in rectangular coordinates, what we meant was the widest of these little rectangles is going down to a width of 0. Here, the widest one will have a width of 0. That's essentially what we're saying here. We're saying that the widest one of these will have an angle that goes to 0. So when we say the norm of our partition, this one just means the biggest angle is going to 0. The biggest angle is going to 0. So we have the limit as n approaches infinity, or the normal of our partition approaches 0, of the sum as I goes from 1 up to n of 1 over 2 f of theta I squared delta theta I. But note that this is just an integral now, because just like in Cal 1, if you take the limit of our sum, that gives us an integral from the beginning to the end. Notice here, our variable of integration was the same as the delta, the small thing that's going to 0. And our boundaries were given by the bounds on that delta x, namely from a to b. So over here, we're going to mirror that. We're going to say, okay, well now it's not delta x, it's delta theta. So instead of a differential with respect to x, we'll have a differential with respect to theta. So this is the integral of 1/2 f squared of theta d theta. And we're going to need some boundaries. And over here, your differential with respect to x. Oh, well, your boundaries are with respect to x. So over here, we're going to have a differential of theta. Oh, okay, so our boundaries will be with respect to theta, from theta 1 up to theta 2, just like that. And this shows us how to find the area of a region in polar coordinates. So let's take a look at an example of something like that. So consider the function given by f of theta. Well, I should say r of theta. Let's just say r, because that's the way it's typically given. R is equal to 4 times the sine of 3 theta. Okay, and the question is simply find the area inside the region. Okay, so here, this is reminiscent to an example that we saw previously. This is a type of rose, meaning it's a shape called a rose. The graph of this is given by, in generic form, r is equal to a sine of n theta, where a is the length of a petal, Sine tells you the alignment of your petals, meaning if this is sine, then one of your petals will align with the vertical axis, with the angle pi over 2. If this is cosine, this will align with your polar axis, with the angle theta is equal to 0. So here this tells you that that one petal aligns with the angle pi over 2. Right? And this tells you if this is odd, n is the number of petals. Right? You say, well, what if it's not odd? What if it's even? If it's even, then 2n is the number of petals. So if this is 3 theta, 5 theta, 7 theta, well, then that means you're going to have 3 petals or 5 petals or 7 petals. But if this is 2, 4, or 6, that means you're going to have 4, 8, or 12 petals. If it's an even, you double that number to tell you the number of petals. Right? Here, if this is sine, one petal aligns with theta is equal to pi over 2. If this is cosine, then one petal aligns with the polar axis. One petal aligns with theta is equal to 0. Right? And here, A is always the length of the petal. So here we can give a very quick illustration of this object. We're not going to graph it in full, but just from this bit of information, this fits a pattern that looks like this. Okay, so that's sine, which means one petal of our rose will align with theta is equal to pi over 2, which is over here, pi over 2. Okay, so now the length of the petal will be 4. Okay, so that means that along this direction, you're going to have a petal that's got a length of 1, 2, 3, 4. Like that. Your petals go back to the pole, and as far away as 4. Okay. Now, because this is the number 3, that's an odd number, you're going to have 3 petals, and your petals are always evenly distributed. You don't have all 3 of them bunched up. You don't have 2 of them bunched together and one on its own. If you have 3 of them, then they will be evenly spread out like this. If you had 5 of them, 2 of them, 6 of them, it doesn't matter how many you have, they're equally distributed. So here the question is, all right, if I have this region, what's its area? And, well, basically we're looking at all of this. We're looking at the area here. Now notice this is nicely symmetric, which means that, yeah, okay, I could find that entire area, but you know what, another thing I could do is just find the area of half of one of these petals, and then multiply by 2, well, that'll give me 1 petal, and then multiply by 3, that'll give me all 3 petals. So here I could just take this 1/2 and multiply by 6. Either one's fine, but you'll find often that limiting yourself to a smaller piece and then multiplying simplifies your arithmetic quite a bit. All right, so here the question is simply, all right, so how do I find the area of just this part? All right, well, let's take a look. We have a result from before that says that the area in polar coordinates is given by this. Okay, so we'll be using that. So the area is going to equal to the integral from theta 1 up to theta 2 of 1/2 f of theta quantity squared d theta. Okay. This part is easy. You're given all of this. Remember, this is given as r, but remember, r is a function of theta. So here, if you're given r is equal to 4 sine of 3 theta, that's the same as saying f of theta is equal to 4 sine of 3 theta. Like that. So here, just plug that in there. So here your area is going to equal to the integral of 1/2. Here that's going to be 4 sine of 3 theta. And the whole thing there is squared d theta. We can write that as, let's see, 4 squared is going to be 16. Sine squared of 3 theta d theta. And of course here, that's half of 16. Okay, so that's going to be 8. So that's going to equal to, and here since that's a constant, let me pull it to the outside. That'll be 8 times the integral of sine squared of 3 theta d theta. This part's generally simple because you know the function. What can sometimes be a challenge is to find these boundaries, to figure out, okay, what's my bounds of integration from where to where? Thankfully for that, we can go to the graph, and if we need to, we can plot a few points. So here we note that this petal starts at the pole and goes out as far away as 4 units, right? This is 1, 2, 3, 4 steps away from the origin. Okay, so let's see if we can't find some angles that do that. Let's see if we can't find some angles that cover that region. All right, let's see. Let me just plot a few points of r and theta. Here, theta, I'm going to go ahead and choose 0. Because, again, I suspect that if I'm at the pole, I'll probably start somewhere over here. All right? So theta is equal to 0. That means that r is equal to 4 times the sine of 3 times 0, which is, well, the sine of 0 is 0, times 4 is still 0. Okay, so I'm at 0, 0, and that's at the pole. Okay, that's where I wanted to start. So now I want to go until I get to this region right here. Okay, so let's keep going. Let me use an angle like pi over 12. You say, why are you choosing an angle you don't know anything about? You don't usually use pi over 12. Well, yeah, but remember, all my angles are being tripled. So here, if I use something that's smaller than usual, it'll triple up to give me something that I'm used to. So here I'll say 4 times the sine of 3 pi over 12. Oh yeah, and I know that. That's pi over 4. So that's going to be 4 times sine of pi over 4, which is 4 times root 2 over 2, which is going to be just 2 root 2, which is not the number 4. If you type that into a calculator, well, what's that going to give us? That's about 2.8. So here, I'm not all the way out to 4 yet. All right? If I am looking in the direction of pi over 12, I'm only going out as far as about 2.8. Okay, so let's keep going. Let's do pi over 6. All right, so that's going to be 4 times the sine of, again, everything's being tripled. So that's 3 pi over 6. Okay, and I know that one too. That's pi halves, and the sine of pi halves is 1. Okay, so that's 4 times 1, which is going to give me 4. Okay, so there we go. If we go from the pole out to something that's 4 units out, that in fact puts us out here at the end of one petal of our rose. So here we've traced out from here up to there, and so that'll actually be a full half of our petal. Here, if we kept going, you'd notice that it wouldn't take much longer for us to get a full petal. If I now use pi, let's see. Let's say pi over 4. Yeah, that should be fine. Let's do pi over 4. And again, I'm just checking to make sure that's an angle that I know how to work with when I triple it. That's going to be 4 times the sine of 3 pi over 4. And I know the sine of 3 pi over 4, that's root 2 over 2. So that'll be 4 times root 2 over 2, which is 2 root 2. And if I use pi over 3, that's going to get me 4 times the sine of triple pi over 3. Well, that's just going to be 3 pi over 3, which is just pi. And the sine of pi is 0. So 4 times 0 will give me 0. And here, if that was a little difficult to see that, okay, I started at the pole and I went up to here. Even if you miss that, well, notice if I keep going a little bit, I'm going to eventually get to the pole again. I'm going to get back to the origin. So here, we can write this as either from 0 to pi over 6, the way we have here. Or if we wanted to, we can go from 0 to pi over 3, get one full petal, and then just triple that. But here, either one's fine. So here I'm going to go with what I originally planned, which is to find that half. And so now I say, okay, well, that's from 0 to pi over 6. All right, so that's from 0 to pi over 6. And that's from 0 to pi over 6. And that's from 0 to pi over 6. Okay. All right, so now we should be able to do that without much of a problem. Here, that's going to be the integral of an even power of sine. So we're going to use the power reduction formula. So this is going to be the integral from 0 to pi over 6 of, instead of sine squared of 3 theta, we can now use 1 minus cosine of 6 theta over 2. Remember, when using the power reduction formula, your angle will be doubled. All right? You reduce the power at the cost of doubling the angle. We can factor out that 1/2. Let's pull that out. That's going to make that 4 times the integral from 0 to pi over 6, 1 minus the cosine of 6 theta d theta. And now that's an angle that's an integral we can take. Because you have a bigger angle, we're going to need to use the chain rule, but now everything's down to a single power of cosine or a constant. So here that's going to give us 4 times the integral of 1 with respect to theta would be theta, minus the integral of cosine of 6 theta is going to be sine of 6 theta. But again, the chain rule has us divide everything here by 6, just like that. And that's being evaluated from theta equals to 0 up to theta is equal to pi over 6. All right, so let's do that. Here, if we plug in 0, notice that all of that's going to become 0. 0 minus 1/6 times the sine of 0. Or in other words, 0 minus 0. So here, plugging in 0 won't make any difference, which is nice. That's one less thing to worry about. But now plugging in pi over 6, well, let's see what happens. That's going to be 4 times pi over 6 minus 1/6 times the sine of 6 times pi over 6, which is 6 pi over 6. Or in other words, just pi. All right, well, we can simplify that. Sine of pi is going to be 0. Okay, so that's just going to go away. That's going to be 0. So in the end, we end up with 4 pi over 6, which reduces down to 2 pi over 3, just like that. But then don't forget, what we found was this area here in blue. That's not the full area we wanted. We wanted the area inside the whole region. So here that's going to be 1, 2, right? Each petal is made up of 2 of those pieces, and there's 3 petals. So I have to multiply this half of a petal by 6 to get me all 3. So here, notice this is the area of one petal, of half a petal. So if I want the area of all 3 petals, I'm going to need to triple this. So here that's going to be 2 pi over 3 times 3, which is just 2 pi, is the area of the whole rose. And that's our result. All right, let's take a look at another example. Same kind of problem. Let's just find the area inside of a region. And here, let's give a different description. Example, go and find the area inside of r is equal to 1 minus the sine of theta. And here we're given a restriction. We're told above the polar axis. When we say above the polar axis, well, whatever your graph is, the polar axis is this one. If you were on the xy plane, you would call it the x-axis. So the polar axis is this one. So what this is saying is, okay, this is going to be some shape over here somewhere. But we don't care about the stuff on the bottom. We only care about the stuff above the polar axis. That's what that means. Okay? So go ahead and give that a try. See if you can integrate to find the area inside of this above the polar axis. Note that you've already been given a function of theta. That's your r. And so that setup should not be difficult. What might take a bit of work is finding your boundaries of integration. And once you have that, it's a matter of integrating to get yourself your result. So go ahead and pause the video, give it a try, and whenever you have a result, go ahead and unpause and we'll go through it together. All right, so let's go ahead and take a look at this object. You may or may not remember this one from a previous section. This is called a cardioid. It's called that because supposedly it looks like a little heart. It looks like one of those cartoon hearts that you see on Valentine's Day. Here, it's not very difficult to trace out the cardioid. So here, what tells you it's a cardioid is whenever you have a constant plus or minus and here this will either be sine or cosine of theta. You shouldn't have a multiple angle here. If this is 2 theta, 3 theta, or anything like that, that's going to be a different kind of function. But if it's just sine of theta or cosine of theta, if you have a constant plus or minus sine of theta or cosine of theta, that's going to be a lemicon. And whenever these two have the same coefficient, if that's a 1 and a 1, or a 2 and a 2, a 3 and a 3, then that's a cardioid. A cardioid is just a special case of a lemicon. So here, with all of this, you get a lemicon. And I think I'm spelling this correctly. And if these two numbers have the same coefficient, here this is like saying 1 sine of theta, because these are the same, you get a special case of your lemicon, and that's called a cardioid. Here, it doesn't really benefit you too much to memorize a bunch of formulas. You can always look those kind of things up, or you can always graph them by plotting a few points. You'll notice here that even if I didn't realize this was a cardioid, or if I didn't remember it, I could always just plot a few points, which I think I'll do here, since I was going to need a few points anyway. So here, let me take theta, let me take r, and just plot a few points. If theta is equal to 0, then 1 minus sine of 0 is 1. Okay, so here I'm 1 unit away from the origin to 1. Okay. And then if I have theta is equal to pi over 4, well, that's 1 minus the sine of pi over 4, which is 1 minus root 2 over 2, which will give me 1 minus root 2 over 2. And that's about 0.3, give or take, about 0.29. Okay, let's see now. Let's use pi over 2. And if I use pi over 2, that's 1 minus the sine of pi over 2. which is just 1. So 1 minus 1 is equal to 0. Okay, good. Here we have, let's do 3 pi over 4. Okay, so that's going to be 1 minus the sine of 3 pi over 4. And the sine of 3 pi over 4 is also root 2 over 2. So that's about 0.29. And finally, and you notice why I say finally, because if we go all the way to pi, this would be 1 minus the sine of pi, or in other words, 1 minus 0, which is just 1. Okay, so now we've gone from this angle over to this angle, and that's 0, that's pi. And so we've gone from here, we've shrunken down a bit to about 0.29, and then once we're facing straight up, we're back at the pole. So this will look like this. And then once you go out to 3 pi over 4, you're going out again about 0.29, and then finally when you're facing all the way to the left, you're going to go out 1 full unit, something like that. All right, so there we go. So yeah, this region will continue down this way, but again, all we cared about was the stuff above the polar axis. So all we want is all of this stuff in here. Be very careful with symmetry. Here, if you wanted to find this area that I've drawn in red, if you found this one piece and then doubled it, that's fine. But now if you said, I want to find the area of the entire cardioid, which here I'm not going to draw it out perfectly. I'm just going to sketch more or less what it would look like. If I said I want to find the entire area, I wouldn't be able to just take this and multiply by 4 because that is different from this one or from this one. I could find all of this and double. That would be fine. Or I could find all of this and double, and that would be fine. But here I wouldn't be able to just take one piece and quadruple it. You do have to make sure that your object is symmetric. Make sure that they are the same. If not, well, you have to go through and find each piece on its own. All right. So here, the area that I want is from 0 to pi. That was something that maybe was implied from before. We want everything above the polar axis. Whenever you have a single angle theta, well, then the polar axis is really just from 0 to pi. If this was something different than theta, 2 theta, 3 theta, 4 theta, that would have been modified a bit. But if it's just theta, well, the polar axis is defined as theta goes from 0 to pi. So either because we read into the context of the polar axis, because we remembered that this was a cardioid, or just because we had a few points that we plotted and drew, we get our boundaries either way. So here the area that I want in red is given by the integral from theta 1 up to theta 2 of 1/2 f of theta quantity squared d theta, which is going to be the integral from, let's just do the whole thing from 0 to pi. This is from 0 to pi of 1/2. We know our function of theta, it's that one right there. So 1 minus the sine of theta quantity squared d theta. And there we go, there's our setup. And now it's just a matter of actually finding out that integral. All right, so let's go ahead and do that. There's a 1/2, which I can factor out. So write this as 1/2 times the integral from 0 to pi. Here, let me go ahead and square all that. And that'll give me 1 minus 2 sine of theta plus sine squared of theta, d theta. All I'm doing is I'm squaring this out to give me this. The 1/2 came out. Here, that's a double angle, and we saw in the previous problem that a double angle, well, we have the power reduction formula. Oh, no, sorry, not a double angle, a squared angle. A square sine of an angle. Here we'll have the power reduction formula. So here that's going to be 1/2 times the integral from 0 to pi of 1 minus the double sine of theta plus, and now here the power reduction formula makes that into 1 minus the cosine of 2 theta over 2. D theta like that. Here I can factor out a 1/2 by doubling everything. Notice this is the same as saying 1/2 the integral from 0 to pi of 1/2 times 2 minus 4 sine of theta plus 1 minus the cosine of 2 theta. Like that. Notice if I distribute the 1/2, that's going to be 1, like I had before, minus 2 sine of theta, and all of this would be divided by 2 to give me all of this. So these are still the same. But now, since I don't have any fractions, I can take this as a constant factor, factor it out, and combine some like terms. So this will give me 1/2 the, I guess I should be 1/4 now. I factored out an extra half. That's 1/4 times the integral from 0 to pi. Let's see, that's 2 plus 1 will give me 3 minus 4 sine of theta minus the cosine of 2 theta. Just like that. And now all of those things are things that we can integrate. So here that'll give us 1/4. Let's see here. The antiderivative of 3 with respect to theta is 3 theta minus the antiderivative of sine of theta is negative cosine of theta. So that negative along with this negative turn that to a positive. So it's going to be positive 4 cosine of theta. And leave it to me to misspell cosine. It's 3 letters and I screw that up. And now over here I'm going to take the integral of negative cosine of 2 theta, which will give me negative sine of 2 theta. But since that's a double angle, since that's an angle that's not just regular old theta, I have to use the chain rule, which gives us an extra 1/2 right here. Right. Normally I'd say plus a constant of integration, but of course this is being evaluated from 0 up to pi. And now we can evaluate. Let's plug in. That's going to be 1/4 times. All right, let's see. That's going to be 3 times pi plus 4 times the cosine of pi. Well, the cosine of pi is -1 minus 1/2 the sine of 2 pi. Oh, but the sine of 2 pi is 0. Okay, so that one's going to go away. Minus, and now let me plug in 0 here. That's going to be 3 times 0. Okay, that's going to go away. Plus 4 times the cosine of 0. Well, the cosine of 0 is just 1. And then here that's going to be minus 1/2 times the sine of 0, which is going to be 0 again. Like that. Here a few things go away. Here anything that's being multiplied by 0 is just 0, so let's not worry about those. Those are just 0. So that's going to give us 1/4. That's going to give us 1/4 times, let's see what's left. We have 3 pi. We have -4. And then we have another -4. Right, -4. Okay, so that's just going to give us 1/4 times 3 pi minus 8, combining my like terms here. And then I can divide everything by 4 to give me 3 pi minus 8 over 4. Or if you prefer, you can write that as 3 pi over 4 minus 2. Either of those is fine. And that's our result. Either of these is an acceptable way to write that. Yeah? All right, so now let's take a look at something that involves 2 different curves. So let's, here we're not going to go through the entire integral. We're not going to get a final numerical answer. Here we're just going to go ahead and set this up, mostly because the final numerical answer is, well, it's just integration. We've seen that 100 times by now. Here the novel part is the setup to this. So consider the curves, there's going to be 2 of them, given by r is equal to 2 minus 3 cosine of theta, and r is equal to the cosine of theta. Okay? Now, while this is not necessary, I'm going to give an illustration here. These can be done entirely through the techniques we're going to use down here, but just so that we can see what it is we're doing and why that would be the correct way to want to do it, let's go ahead and draw a quick illustration here. Okay. R equals cosine of theta. That's a circle with a radius of 1. It's going to touch the pole and it's going to go out as far as a distance of 1. So let's see, 1, 2, 3, 1, 2, 3, 4, 5. Okay, so here we have a small circle. It has not a radius, it has a diameter of 1, I should say. It has a diameter of 1, and it touches the pole right here. So that's this curve here. Now we have another curve. That's this one. This is a lemicon, and it'll look something like this if we graph it out. And it'll go up and out. And then here it'll make a sort of a, oh, what's the word for this? I guess a loop. It'll kind of loop around this way. Oop. Like that. And then come out to here. All right. So the question in this is to find the area that these two have in common. So the language is find the area of the common region bound by both curves. Okay? So what we're doing is we're saying, okay, I have this lemicon, I have this circle, and in here I have a small little bit of area where they overlap. Find that area. Okay. Well, all right, so let's go ahead and find that area. The very first thing we're going to need to do, though, is we're going to need to find where these intersect. If we can figure out where they intersect, that'll help us in setting up our boundaries of integration. So here, let's find out where these intersect. To find where two things intersect, we do the same thing we always do, going back to algebra. To find where two things intersect, you set them equal to each other. Okay. So here we say r is equal to this, and r is equal to that. So where they intersect, we'll set the two r's equal to each other. Yeah? Set the two functions equal to each other. So first of all, let's find the points of intersection. All right, and here, just set these equal to each other. 2 minus 3 times the cosine of theta is equal to the cosine of theta. Here I can add 3 cosine of theta to the other side. That'll give me 2 is equal to 4 cosine of theta. And then divide both sides by 4, which gives me 2/4 is equal to the cosine of theta, or more simply, cosine of theta is equal to 1/2. And we know a couple of places where that happens. Here, let's say theta is equal to pi over 3. Pi over, yeah, that's right, pi over 3. And 5 pi over 3. 5 pi over 3. Just like that. Now here, note that we do have other values that would work. We could also say negative pi over 3 and negative 5 pi over 3 and so forth. We go forward and backwards. But here, let's see if that's sufficient. All right, well, what I want to do is I want to find this area in here. Notice that, again, I have a bit of symmetry. So if I can just find this area up here, that'll be the same as this area in here. Now you might say, well, wait a minute. I think that little thing, that kind of looks like a petal from a rose. Is that symmetric? Maybe, but we can't count on that. Because notice, this outer edge is bounded by the edge of a circle. This inner edge is bounded by this lemicon. And even though they look similar, because they have different formulas, they have a different shape to their curve, this part down here might be slightly bigger or slightly smaller than this part up here. So be very careful here. You can't say, oh, I'm going to take half of this and then double here to give me the full part here. What you can do is you can say, oh, look, that's bounded by a lemicon in a circle. That's bounded by that same lemicon in circle. So here, maybe I just find this area and then double. So let's go ahead and do that. We're going to find the area of just this part. Find this area and double. Okay, so let's find that area. I'm going to go ahead and take that illustration and zoom in just a little bit. So it would be something like this. I'm going to consider just that little part right there. And again, these might be symmetric or they might not. This area up here might be bigger than this one, or maybe vice versa. So here, there's no reason to assume that they are the same. All right. So here, note that if I'm trying to draw this out using polar coordinates, if I start from here and I start going this way, notice that I'm going from my pole to my purple line. But once I get to this angle, if I go from my pole out to the edge of my region, I'm no longer going out to the edge of my purple line. Now I'm going out to the edge of my blue line. So what that means is I'm going to need two different integrals. One integral will describe this part right here from the pole to the purple line. And then once I get to this boundary, which I already know, I found was pi over 3. Then once I get past that, I'm going to have to use a different integral to find this area from the pole to the blue region. All right? Here I'm not going to use 5 pi over 3 because that would have been this one down here. And here I'm satisfied with finding this upper part and then doubling. All right, so let's go ahead and set up those integrals. In fact, see if you can do it. See if you can find, now here you're going to need two integrals. It's going to be the integral from, theta 1 to theta 2, and then separately there'll be another integral, and it's going to be integral plus another integral. See if you can do that. See if you can set up both of those integrals, one to describe this region, one to describe this region. I'm not asking you to integrate. I'm just asking you to set it up. Once you have a setup, go ahead and unpause the video, and we can go through it together. All right, so let's take a look. I'm going to make it color-coded here. So first of all, I want the integral from here to here. All right, well, note that this starts at the pole. And so if it starts at the pole, we're going to need to find where this purple curve is equal to 0. Okay, so just a little more arithmetic on that part. Let's see here. We have this curve in purple is given by r equals 2 minus 3 cosine of theta. But here we want this to start at the pole, right? That's where we want to start counting from. This curve is going to start from the pole and go outwards. We know that the final angle, when it reaches this point, is going to be pi over 3. Okay, so that's one of our boundaries. But we still need the initial boundary. We still need to see what's the lowest value of theta that starts us from down here. Okay, well, that's going to be to find where this purple curve is at the pole. That's bad grammar. Let's say for what theta is r equal to 2 minus 3 cosine of theta at the pole. Well, remember, the pole is where r is equal to 0. Okay, so then let's set r equal to 0. It's going to be 0 equals 2 minus 3 cosine of theta, which is the same as saying, well, let's go ahead and add the 3 cosine of theta over to the other side. 3 cosine of theta is equal to 2, which is the same as saying the cosine of theta is equal to 2/3. Okay? This is not going to be a nice number, which is why I said we're going to mostly set this one up. We're not actually going to do the integral because, well, the integral here in this one gives you a really not a nice number. But for us, it's sufficient to know how to set this up. Here, we can take the inverse cosine of both sides, and that's just going to give us that theta is equal to the inverse cosine, or if you like the language, the arc cosine of 2/3, okay? Which is somewhere between pi over 4 and pi over 3. And you say, you know that? No, before I did the problem, I worked out a few notes ahead of time, and that's just one of the things that I worked out in my notes. That answer is somewhere between pi over 4 and pi over 3. I don't know that off the top of my head. Okay, and neither do you. You don't need to know that off the top of your head. That's your result. That's how you know you're at the pole, if you're at this angle. Oh, okay, so this area here is going to be the integral from, that's the inverse cosine of 2/3. And you might say, well, what is that? Well, that's it. It's the inverse cosine of 2/3, right? You can punch it into a calculator and get a decimal approximation, but it doesn't matter. That is the exact boundary. That's how you know you're exactly at 0. And if you're at the pole, if you're at the origin, okay, well then that's there. And now as your angle gets bigger and bigger, you sweep out more and more of this area. And you're going to continue to sweep out this area until you get to the angle pi over 3. Okay, well now, the rest of this is just from our formula. It's the integral from theta 1 to theta 2 of 1/2, take your function and square it. And you say, well, I have two functions. Which one? Well, the one you're currently using. Currently, you're using this one for the lemicon. Right? So we're going to be using this formula here. So 2 minus 3 cosine of the angle theta, quantity squared d theta. And that's it. That'll give you that area in there. Okay. Now to find the area of this other part, notice that once you get past this line, well now if you're taking an integral, now you're going from the pole to this blue edge, which is the edge of that circle. Oh, okay, so now that's going to finish tracing out the remainder of this region. But notice now we don't have this lemicon curve as our outer function. Rather, now we have this curve of our circle. Okay, well, let's see here. I know that's going to be pi over 3. And that's where one leaves off. That's where the next one picks up. So that's going to be the integral from pi over 3 up to. Here, this one's a little simpler to do. We want to figure out where this circle is going to hit the pole. And that's much simpler. Here, if we're going to hit the pole, we want r to equal to 0. Okay, so what angle gives you cosine of that angle is equal to 0? Well, pi over 2, right? Or 3 pi over 2, but that will put you down here in this region. So here, pi over 2 is going to be up here. If that's a little hard to see, you can always trace out a few points. You can always start from theta is equal to 0, theta is equal to pi over 4, pi over 3, pi over 2, and you'll see that as that angle goes from 0 to pi over 2, it'll sweep out that upper half of that curve, upper half of that circle, so that you'll hit the pole when theta is equal to pi over 2. So there we go. From pi over 3, from that red line, to pi over 2, when you get back to the pole, that'll sweep out this entire region here. And that's also going to be 1/2 times your function squared d theta. But now your function is the function that gives you the outer curve of that circle, which is cosine of theta. Just like that. Now note, we have two different areas. We're trying to find the whole thing, so we're going to go and add those. And then don't forget, this is only half of our region, so we're going to need to double this whole thing to give us our result. All right? This was that purple region. This was that blue region. Added together, that gives us that upper region, and then doubling it gives us that bottom region for our total. So this is our setup. I'm not going to go through and integrate this because note this one is going to be a very long computation with a very not nice number. And at this point, I mean, we've gone through all of chapters 5, 7, 8, 9, and most of 10 here. You've seen integrals done over and over again. For this section, the concept of primary importance is, can you interpret these graphs and can you describe things in polar coordinates? For those of you who go on to Cal 3, polar coordinates, as strange as they may sometimes seem, are going to be labor-saving devices. There are going to be some integrals that, if you try to do them in rectangular coordinates, are going to be, I mean, impossible may be the wrong word, but practically impossible. Something that's far too difficult for anyone to do or even visualize. And in polar coordinates, it's so simple that you wouldn't even need a calculator. Just by inspection, you could find the integrals. So polar coordinates are a nice labor-saving device. So for this section, what we want to do is make sure, again, you can interpret them and you can describe them. Okay. Finally, the last thing that we're going to look at in this section, we're going to look at a theorem without any proof given to this theorem. It has to do with the arc length. So theorem. Let's begin with a function that is defined in polar coordinates. Again, r is equal to f of theta. let r equal f of theta, where f is, or I guess I should say has, a continuous derivative on the interval from alpha to beta. So you have r is equal to f of theta. F is going to be continuous and is going to have a continuous derivative on the interval from alpha to beta. If your theta exists anywhere between here and here, you know your function has a continuous first derivative. Outside of that region, maybe it does, maybe it doesn't. We don't really care. The length of the arc given by r equals f of theta from theta equals to alpha to theta equals to beta is given by, here they use s for arc length, I'm not quite sure why, of the integral from alpha to beta of the square root of f of theta quantity squared plus f prime of theta quantity squared d theta. In its alternate form, it can also be written as the integral from alpha to beta of the square root of r squared, since f of theta is equal to r, plus the derivative of r with respect to theta. So dr d theta quantity squared d theta. Those are equivalent, just alternate notations. It's not like, oh, this can be shown to be this. No, this is just an alternate notation. We can either use the function notation or we can just call it what we usually call it, which is r. The proof of this one is omitted. However, I will start you off. For those of you who are interested in further mathematics, Cal 3, differential equations, linear algebra, and so forth, you might try this out just as a test of your abilities to try to reason your way through a theorem. Just to start this off, go ahead and recall that given a curve given a parametric curve, given a plane curve, defined by the parametric equations x equals to f of theta, here let's say f of t, that way we don't confuse it with the theta from above, and y equals to g of t. So you have a plane curve given by a couple of parametric equations. We saw in a previous section that the arc length on an interval for t on an interval from, let's say, a to b, then the arc length of the curve is given by the integral from a to b of the partial, of the derivative of x with respect to t quantity squared plus the derivative of y with respect to t also quantity squared, all under a square root dt. Okay. So we have the arc length formula for a parametric equation, or for a plane curve defined by parametric equations rather. And also recall, so here I'm just going to remind you of two things. Recall this, and also recall that when we switch to polar coordinates, of course, x and y are given by a couple of parametric equations. Namely, they're given by r cosine of theta and r sine of theta respectively, which can be written as r equals f of theta cosine of theta, because after all, r is a function of theta, and y can be written as f of theta sine of theta. Those two facts can be put together to give you this result up here. Namely, here's your set of parametric equations. Here is your arc length for use with plane curves defined by parametric equations. So now find the specific case of this using these specific equations. All right? So the proof of this is, I've always wanted to say this, the proof of this is left to the reader, or the listener in your case, yes? The remainder of the proof is left to the student, if you like. This is a decent practice in making sure that you're used to using this notation. It's decent practice in being able to manipulate these to make sure that you understand what each component means. And it's just a nice way of practicing a proof which is not simple, but accessible. So if you're interested in this kind of thing, go ahead and give it a try. If not, well then, let's just look at an example, yes? Let's consider a curve given by r equals 2 times a cosine of theta. So we're going to go ahead and find the arc length of this on the interval from minus pi over 2 to positive pi over 2. All right. So let's see how that works out. So given our result from our previous theorem, we know that the arc length is simply going to be given by, so here arc length is given by the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta, like this. Okay, so let's go ahead and find all those things and pop them in. Okay, here, this is in previous examples, these boundaries are hard to find, but here they just give them to you, which is nice. So here, that's the integral from minus pi over 2 to positive pi over 2 of the square root of, well, we know what r is, it's given to us. That's going to be 2a cosine of theta, and that's being squared, plus we need to find the derivative of this with respect to theta, which isn't too bad. That's a constant. So the derivative of a constant times the sine of theta is that constant times negative the sine of theta. So the derivative of 2a cosine of theta is negative 2a sine of theta. That whole thing is squared and integrated with respect to theta. Okay, so now we can go ahead and take each of these and square them. So that's going to be the integral from minus pi over 2 to pi over 2 of the square root of, well, let's see. If we square each of these things, that's going to be 4a squared times the cosine squared of theta plus, here, the double negative will cancel out, so that'll be positive 4a squared times the sine squared of theta, all under a square root d theta. Notice I have a common factor of 4a squared, so I can write this as the integral from minus pi over 2 to positive pi over 2 of the square root of 4a squared, and when I factor out 4a squared, I get cosine squared of theta plus sine squared of theta, d theta. But now, think back to trigonometry. The sum of the squares of sine and cosine are equal to 1. This is going to be the Pythagorean identity. So this is the integral from minus pi over 2 to positive pi over 2 of the square root of 4a squared times the number 1, d theta, which is the integral from minus pi over 2 to positive pi over 2. Well, here I can take the square root of this, right? Square root of 4 is just the number 2. Square root of a squared is just the number a, and the square root of 1 stays 1, so we don't worry about that. And that's going to be 2a d theta. And now that integral is really simple to take, because remember, 2a is a constant. And if I take the integral of a constant d theta, I just get the constant times theta. So here that's going to be the integral of, not the integral, I've already taken the integral, It's going to be 2a theta, evaluated from wherever theta is equal to negative pi over 2 up to where theta is equal to positive pi over 2. You notice here I actually wrote the name of the variable. Normally I just write from negative pi over 2 to positive pi over 2. That's a good habit to get into whenever you start having things with multiple things that could be variables. Here, if you were a little absent-minded, you might plug it in for a instead of for theta. This will become an even more important habit in Cal 3 for those of you who go on to the next class, because in Cal 3 you actually will legitimately have multiple variables simultaneously. Here a is a constant and theta is a variable. In Cal 3 you'll legitimately have r and theta both as variables. So here it's a good habit whenever you have two things that either both are variables or even look like they could be variables, you want to label what you're plugging in so that you don't accidentally substitute into the wrong place. So here we can write this as 2a times pi over 2 minus 2a times negative pi over 2, just like that. And now we're going to take, that's a double negative, so that makes it a positive. So here that's 2a times pi over 2 plus 2a times pi over 2. Here these 2's just divide out. So that's going to be a pi plus another a pi is 2a pi. And there's our result. That's the arc length of that curve. Incidentally, what does that look like? Well, if you graph this thing right here, that's a circle. All right, so here we could spend the time to graph point by point, but here let's just very quickly, if theta is equal to 0, cosine of 0 is 1. 1 times 2a is 2a. So if you're facing in the direction of the polar axis here going to the right, you're going to go 2a units forward. So that's 2a. Okay? And that's going to be the furthest reach of your circle. So here, if we plot a few more points, you'll actually find that it gives you a full circle that goes back to your pole and between here and here. Okay? So that is a circle. All right, so now we found the arc length from negative pi over 2 to positive pi over 2. Again, if you take the time to plot your points, you'll find that from negative pi over 2 to positive pi over 2 actually just goes once around your circle. Okay? If you take negative pi over 2 and plug it in right here, the cosine of negative pi over 2, well, that's going to be 0. So I start at the pole. If I go to 0, well, that's going to take me out to the furthest reach. And then if I go to positive pi over 2, the cosine of positive pi over 2 is also 0, which brings me back to my pole. Again, you could plot a bunch of points to convince yourself of that, but that is what you have. Here you're starting at the pole. Halfway in between, you get out to here. And then once you reach positive pi over 2, that brings you back to your pole. So really, this is just one full revolution of this circle. Oh, well, if the distance from here to here is 2a, that means that the radius of this circle is just a. From here to here, right? If all the way across is 2a, then halfway across is just a. So what this is saying is I want to find the arc length around a circle of radius a. Oh, okay, so really this is saying find the arc length of a circle, around a circle of radius a. Find the arc length around a circle of radius a. Well, yeah, but the arc length around a circle, that has a special name. That's called the circumference of the circle. So really, this question was asking, find the circumference. Of a circle with radius a. Okay, well, let's see. The circumference of a circle is 2 pi r. Oh yeah, but for r we're using a. Okay, so 2 pi a. This right here is the proof of the circumference of a circle. Up to now, if you ever saw that in geometry or in algebra or anywhere else, that was just a sort of matter of fact. Oh yeah, no, the circumference of a circle is 2 pi times the radius. You just you were told that, but you were never given an actual proof as to why that should be true. In fact, here it is. The arc length around a circle of radius a is 2 pi a. Usually we use the letter r here, but in this instance, the letter r was taken by some other variable. So here we use a different letter. Okay, but the circumference of a circle of radius a is 2 times pi times the radius a, which does confirm something that we've known since, I don't know, grade school, I believe, right? The formula for the circumference of a circle. And that brings us to the end of our section. So let's see, for an assignment, let's have you try section 10.5, 7 through 17 odd, and 27 through 33 odd. 7 through 17 are simply going to ask you to find an area inside of a region. They're going to give you a region. They're going to give you the boundaries. It'll be a nice, simple exercise in integration, just making sure you know how to use these formulas. These here will ask you to find the intersection of curves, essentially saying set these two curves equal to each other and solve. All right? And then go ahead and try problems 45, 55, and 57, which are similar to the ones we've seen today, and they are the problems in full. These are nice small pieces which they guide you through. Here, these three are bigger, more full problems where you'd have to sort of guide yourself through them. All right? So if anybody has any questions, comments, or problems, please make a note of them. You reach out to me and I will get back with you as I can. And I hope everyone has a nice day.